now that we've got the careful statement of Rolle's theorem, I want to show you an example of using that. It's going to actually combine it with IVT. It's a classic example. We've got an equation that we really wouldn't have any prayer of solving algebraically exactly because we've got a transcendental function, sine, cosine, log, exponential, and polynomials mixed together, and not in a way where they kind of break up easily. But we can actually be sure of the number of solutions. We can actually show that there's exactly one solution to this guy. And one of the tricky things here is that to show exactly one often is two things. Often you show that there's at least one, but then you separately, with a different tool, show that there's at most one. So at least one, we're going to use IVT. This is just straight up review of use of IVT. We want to show that sometimes this is negative and sometimes this is positive. Okay, and of course it's continuous. So note we let f of x be that left-hand side, so we can name it and talk about it explicitly. F is continuous. It's a polynomial plus a sign, one of the trig functions that doesn't involve division. Okay, so IVT plausibly can be activated, and then the only other thing we need is two values that bracket 0. So like f of minus 10, for example, is minus 2000 minus 30 plus sine 2x. Well, the sine 2x is at most going to bring us 1 closer to 0. So that's less than or equal to minus 2029, and that's less than 0. Similarly, f of 10 is 2030 plus sine, oh yeah, I should have put in, sorry, minus 20 there. But whatever the heck it is, that's greater than or equal to plus 2029, which is greater than 0. Okay, so that activates IVT, and therefore we know that there must be somewhere it crosses because it's gone from negative to positive, and we're going to get a crossing. So by IVT, there is some c with f of c equals 0. Now, we want to show at most one. So here we're going to use an absolutely logically equivalent form of Rolle's theorem, but I'm going to say it as, just write it out. We're going to use this tool, okay, just an equivalent form of Rolle's theorem. If, first of all, you can't apply either version, continuous on a closed interval and differentiable on the open interval. It's very rare that you take it, well, it's rare that you take advantage of the fact that you don't have to check differentiability right at the endpoints, but it's nice to know, okay? Blanket hypotheses are the same, okay? And f prime of x is never 0. In the interior of the interval. Well, then let's think about it. Rolle's theorem says if f of a were equal to f of b, then I would get a 0 for the derivative. If I'm not seeing a 0 for the derivative, and all the other hypotheses are satisfied, there's no way that it can have the same value. Because if this were true, all of Rolle's theorem would be activated, and I'd get a 0 for the derivative, I'd get a turnaround, but I've actually verified that I'm not getting any turnarounds. Okay. So, in other words, for such a function f, if f prime never vanishes, it can never achieve the same value twice. It's one-to-one, in other words. That's a nice thing to know about a function. Okay. Now, we could also make this, well, there's two versions of this which use stuff from 4.3. It's a little bit of a more precise version of this. I might as well mention, and we could use one of these here, but you could also just quote Rolle's theorem directly. We know that if f prime is always greater than 0, then f is increasing. Okay. Again, never hits the same value twice. If f prime is less than 0, then f is decreasing. And will never hit the same value twice. So you can say, if you really know the sign of f prime, then you can be a little more specific. But it's kind of nice that Rolle's theorem is a little bit more powerful, because all you have to know is that it's just not 0. Now, I'm going to show you an example where we're actually going to, in our example, let me remind you of the function we defined. We're actually going to be able to show that this derivative is always positive. Oop, you're not seeing that. Okay, so let's take the derivative. 6x squared plus 3 plus 2, remember the chain rule, cosine 2x. Okay, now here's the thing. Whenever you're doing inequalities, okay, if you have some quantity, some variable quantity that's always greater than or equal to some constant, you can just piece by piece replace those in a greater than or equal to statement. 6x squared is always greater than or equal to 0. Always look out for the fact, the most basic inequality, that even powers of any real number are greater than or equal to 0. That's often what's going on in these kinds of problems. Plus 3, plus, and we know that cosine 2x is at least minus 1. So this whole thing is at least minus 2. So we can just put in the minus 2 there. This is bigger than this. This is equal to this. This is bigger than or equal to this. So the sum of these guys is greater than or equal to the sum of these guys. And that equals 1, and that is strictly greater than 0. You want strictly. At some point, you want to say it's bounded away from 0. It's the whole point. It can't actually come to a rest and actually get to 0 derivative somewhere, because then the whole thing falls apart. So in fact, we've really shown that it's an increasing function. Everywhere. Not even just on some particular interval. Sometimes you can do it where it's just on the interval of interest. Okay. And so we could use the kind of tighter version. It's like, actually, we know that this is going uphill. It's not just that it never reaches the same horizontal line twice. It's actually going uphill. But if you just want to sort of say, hey, I want to focus on using rolls as the tool, I just know that f prime of x is never 0. So very roughly, this thing has some wiggles to it, but it's never less than slope 1, and sometimes steeper. That's not a very good graph of this function, but it gets the idea. It goes from negative to positive, so IVT is activated and you get a crossing. And it's always uphill, activating rolls, or our characterization of saying, hey, this is an increasing function. And so remember, this says we got at most, or at least 1, sorry. And this says at most 1. Put that together, you say there's exactly 1 solution. And that's a nice thing to know about an equation.